Thanks. Yeah, hi. So I want to talk to you about something cool, I think, that I've been working on with Patrick Bahr and Graham Hutton recently. And yeah, the idea is basically this. It's calculating type checkers. So maybe you've seen some of the work in calculating compilers, calculating other programs. There's this really nice example of you can calculate a fast reverse function from sort of the naive inefficient definition. But don't worry if you've not seen any of this before, because I'm going to explain it all as we go along. This is a functional Perl, and for good reason. I think that the best way of presenting this is a story, really, of how it all works. And the reason for this is that hopefully when we get to the end, it's going to be easier to understand, for one thing, but also more satisfying of a conclusion. So yeah, let's get started. Types describe the semantics of your program, right? So the type of your program is going to tell you something about what kind of values it's allowed to evaluate to. And the lack of a type can also tell us something like maybe it's going to fail to evaluate, or maybe we just don't know if it's going to evaluate or not. Type checkers are programs which can tell us such a type if it exists. So hands up if you've written a type checker before. Quite a lot of you. Yeah, I've written a few myself, and the process varies a bit, but it probably looks something a little bit like this. So you're going to start by defining your language, probably write down some typing rules, which are going to involve some various Greek letters and some horizontal lines and this sort of thing. And then you can write your type checker, which is going to be a function, probably. And this is the actual type checker, sure. Ideally, you would then prove some correctness of this type checker. Admittedly, I don't usually do this, but it would be nice. So I guess a bit of an aside, maybe you've seen some of these papers, or maybe you can read them from where you're sitting. There's quite a lot of work in this idea of calculating compilers from specifications. So the idea is that you can start with a semantics of your language, and you can derive a compiler for it mechanically as well as a virtual machine for these semantics. I think this is a really cool area, and we were just sort of wondering, like, can we apply this to type checkers? Can we derive type checkers mechanically via calculation? And yes, you can. You can actually do that. And so in this talk, I'm going to explain our techniques for doing this, and how maybe you can apply these to your own type checker needs. So yeah, to set this up, you need a language. For the purposes of this presentation, I'm just going to use a really simple language. We've got values, we have addition, and we have conditionals. This is like a if condition, if true, else false sort of thing. So it has three expressions with it. We need to describe how to evaluate this language. Again, it's really not hard for this language. It's just a sort of a compositional semantics that we're writing down here. So to evaluate an addition, you evaluate the subterms, and then you add them together. So the third thing we need is the equation that we're solving. And so we want to kind of say, what would it mean to have a type checker for this language? A natural thing that you might want to write down here is this one. So you see on the left-hand side, we are evaluating the expression e, and then taking the type of this value. T-val takes the type of value. And on the other side, we're just applying our type checker, which is called texp. And this is an equation with three unknowns. I'm going to have all the unknowns in italics just to make it clear. T-val, texp, which is the type checker, and also the set of types themselves. So that's three unknowns, one equation, which is not necessarily ideal. But actually, we can have a look at two of these to start with. So, right, what are the types? quite a natural thing to do is to just say that each value constructor gets its own type. So here we're going to have integers, booleans, and this error type. And then this gives, again, a very natural definition for our tval function. It's worth noting that you can actually calculate these things as well. I'm going to skip over those details, though, because it's kind of boring and obvious. But it is also worth noting that we can, if we need to, refine these later during the calculation. So this is sort of just a starting point. But the great thing is that this leaves us with just one unknown, which is this tx, which is our type checker, which is what we want to calculate. You actually can't solve this, though, unfortunately. It's too strong of an equation. Some of you might have realized this already. The reason relates to this question. And OK, so what is the type of this program here? If true, then 5, else false. In most languages, this is going to be a type error because the two branches have different types. But our equation said that the type checker has to give us the same type as evaluating it and then taking the type of that value. In this case, the value is 5, its type is an integer. The type checker would have to look at the values. It would have to do evaluation, and this is sort of no longer a type checker, really. We don't want this behavior. You can, therefore, really think of a type checker as more of a partial function. It's allowed to fail. It's allowed to say, I don't know, if it doesn't know. And the natural way to do this in Haskell probably is using the maybe monad. This actually works. So, you know, we could reframe the specification using this type for our type checker. But the problem is that now we're working in this monad, and it makes the equation a bit clunky. It makes the calculations a bit more long-winded. It's not very nice. But there is another way to do this, actually, which is a bit more elegant, I think. And that is that we place our types in a partial order. So we say that any two types are incomparable except with error, and error is the smallest type in this order. So error is less than anything else. And you know, in this way, you can sort of look at this as an information ordering, right? So if one type is less than another type, it is less specified than that type. It contains less information in some way, and this lets us write a slightly different specification as an inequality rather than an equation. So here you can sort of see that the type checker, it might give the type that we're looking for, but it's also allowed to give something which is less specified. In this initial set of types, that's just going to be error, but you could look at you know, more complicated type systems as well. So with that, we can try and start these calculations. And I like to say it's sort of just like in maths. It's a bit of a lie. But it's sort of just like in maths. Essentially what we're doing is we're trying to solve this inequality by induction, specifically what we call constructive induction, which is we're solving it, but while we're solving it, we're allowed to introduce definitions, defining clauses of this tx function, or of any unknown really, in order to make the proof go through. So let's start off in very much the same way as sort of the standard compiler calculation literature, really. We're going to start on one side of the equation. I'm going to do the conditional case here with if, but you know, same goes with any of them, really. And we want to transform this into the right-hand side of the equation by potentially applying induction and also introducing definitions of our type checker. So we can firstly apply some definitions here. We know how a val is defined, and this gives us this term here. We really want to be applying induction, and these calculations are primarily driven by this desire to apply induction. In order to do this, we need a t-val of eval of something, right? We need t-val and eval touching because this is our induction hypothesis. It's that t-val of eval is greater than tx. But we don't have this. But what we can do is we can just sort of postulate this function, right? We can just say, imagine we have some function. I'm going to suggestively call it cond prime. And I'm just going to say that this function is exactly what we need to get this term in the form where we have lots of t-vals and e-vals next to each other, which is very convenient. You can see that this step we're doing, actually this is a less than the previous term, but this is okay because remember our specification is also defined as an inequality, so all good so far. Now we can apply our induction hypothesis 3 times on x, y, and z under the condition that this con prime, which we've yet to define, is monotonic. And that's just because, again, we're in this partial order. We need to apply it inside the function's arguments. But now we're at a point where we can just sort of say it like, okay, this is a definition of tx at if x, y, z. And by doing this, we find ourselves at the right-hand side of the equation. And so this has given us one defining clause for our function, for our type checker. And you know, we can also, well, we have to calculate this con prime. I won't show you the calculations here. They're not that hard. And we get this. And you know, this is probably what you'd expect, right? This is if the 2 branches have the same type, then the conditional has that type. Otherwise, it is a type error. And like, okay, this is maybe not entirely satisfying. I'm not that happy with this for 3 reasons. Firstly, it feels a little bit weird to have just said, okay, imagine we have this con prime which has this property. You know, there's sort of some creativity there, and we don't want to be clever, ideally. And actually, the second problem here is a little bit similar. It's during the calculation of con prime, which I haven't shown you, we have to introduce a lemma to make this particular calculation go through as well. And it's from this lemma that we get the body here, which is if the 2 types are the same, it's that type, otherwise it's an error. And again, we don't want to think about this. We don't want to be clever. We don't want to be creative. We just want this to come for free, right? And finally, there's this annoying sort of niggly bit of we have to prove monotonicity of cond prime, and same goes for add prime when we do the add case, and this is annoying. And you know, again, it's not a hard proof, but it's not totally trivial. It's not free. So yeah, in the rest of the talk, I'm going to explain how we can solve each 3 of these problems in sort of a more elegant way. So yeah, let's come back to our semantics. And as I mentioned, these are compositional semantics. This is you know, it's a fold, basically. It's we evaluate the subterms and then throw these into a function that does something with them in a non-recursive way in and of itself. As a result, we can write it as a fold. And actually, we can write the type checker as a fold as well. The type checker that we came up with in the end does happen to be a fold. I say happen to be, okay. It's not just happening to be, but cool. Here's our specification again at the bottom. And let me just substitute these definitions in, right? So we're going to write this in terms of the folds instead. Maybe this reminds you of something. Maybe not, but maybe. Let me, again, suggestively put something on the screen. This is the fold fusion law. In Haskell, you can fuse a function into a fold by coming up with some new folding operators subject to certain conditions. And these are sort of like distributivity conditions, you could say. These are them. And actually, you can generalize this to a partial order, so to an inequality rather than an equal sign here, under this condition that f prime, this folding operator, this new one, is monotonic. And of course, we can also generalize this from lists to any type, well, any algebraic data type, right? Any inductively defined type. For example, our expression type. And maybe you can see it now. This is exactly exactly our specification. If we substitute t-val for h and also for this val prime operator, it's exactly our specification. And the great thing here is we now know that if we can find a const prime that satisfies, well, okay, there are five conditions here. Any const prime that satisfies these 5 conditions also satisfies our specification. So I guess you can look at this as, we've sort of divided the problem up a little bit, and we can look at these separately, which is great. But more importantly, for me at least, this has fixed our first problem. We now know where const prime came from. It came from the fact that this is just full fusion. So we can come back to calculating things. Let's try and calculate this const prime from this when I say second, it's actually the first one's a bit boring. So second condition. This is, again, the definition of this const operator. This is defined in the semantics of these conditionals. And it's defined by pattern matching on this first argument. So it really only makes sense that we're going to solve it by induction on this same argument, right? So let's do that. On the same cases, we can start with this case where the condition is this is true. And the goal here really is that we're going to start with this inequality that we're trying to solve, and we're going to try and find some definition of const prime which implies that this is true. So firstly, we can just substitute our x in, of course, and we know some definitions, so we can apply the definitions of const and of t-val. And this is kind of looking like a definition already, in a way, by pattern matching. What we can do actually is we can make this strengthening step. So this is now a reverse implication. So this inequality implies the one above it. And what we've done is we said, I don't really care that I have a t-val z and a t-val y. Let's just say, okay, what if this is true for any t and any t prime? The motivation for doing this is that this just looks even more like an actual defining clause for this const prime. Like, say you flipped around this inequality and changed it for an equals, this is a defining clause. Okay, cool. And actually, this pretty much goes exactly the same for all of the other cases that we look at for x. So here's the integer case. I won't show all of them, but here's the integer case. It really is exactly the same. We substitute x in, we apply const and t-val, and then we make this same strengthening step again. So what we're left with is 4 inequalities. We still don't have a definition, but it's looking a lot closer to one, perhaps. And actually, these are sufficient, right? Again, if we can write down a definition of const prime that satisfies these constraints, we have a definition of const prime. We can make some transformations to begin with, actually, without really thinking too much at all. Firstly, we can change, you see, these inequalities here for equal sign, because if something is less than error, it is equal to error. These two are now defining clauses, right? But we can't use the first two as defining clauses yet because the patterns will be overlapping. You see the right-hand side on each of these is exactly the same. But again, we're working in a partial order. In fact, we're working in a partial order with a bottom, and therefore we can use the greatest lower bound. And this lets us combine these 2 inequalities at the top into this one inequality at the bottom. And this is actually just the definition of the greatest lower bound, right? It's, this constraint here is equivalent to the 2 constraints at the top. So we now have 3 constraints rather than 4. And this is great because this lets us literally just write down the best possible definition in some sense, the sort of largest possible definition satisfying these 3 constraints. And we just do that by changing all of the inequalities for equals signs. And also we can combine the last two because they both have error. Okay, cool. This is now our definition of con prime, this operator which finds the type of a conditional. And actually, this is functionally identical to what we had before when we did the whole calculations in the previous way, because this definition of the greatest lower bound, you can just read off from the graph that we had of the ordering that it is, if the types are the same, it's just one of these types, and otherwise it's error because that's the bottom value. But the great thing is that this time we didn't have to be clever. We didn't have to sort of think like, oh, okay, let's write down an if here, and let's say like, okay, let's put this t equals t prime here, and it was completely natural. It fell out of the calculations, and this solves our second problem, which was that we didn't want to think of lemmas in general, this one specifically. Great. Monotonicity is still kind of annoying though. So, 2 out of 3 so far, but actually this monotonicity proof that we have to do for each of these operators takes more time than I would like. So let's have a look at that. And sort of, let's, I guess, take a bit of a roundabout way to looking at this. If we come back to these constraints that we calculated in the previous step, you remember after doing this, this sort of reverse implication weakening, strengthening, not weakening, sorry, step, we get these 4 constraints, and I just want to write down a function that satisfies these. It doesn't feel like it should be that hard, right? I just want to say like, okay, if the first argument of my conditional is an int, then just give me an error. Otherwise, don't worry about it. Just ignore this clause, ignore this case. It doesn't matter. And equally, if it's an error, give me an error. If it's a Boolean, I want it to give me t and also t prime. And but otherwise, ignore it. Don't worry about this case. And I'm trying to write this, but I can't quite write it because Haskell doesn't let me. I have to put something where these question marks are. Let's call these clauses, right? And I'm combining these with the greatest lower bound. Reason being, if I get an error in one of these, then I want the whole thing to be an error. Simple as that, really. Yeah, but we can't write this down because we don't have a type that we can write here. We want something that's sort of invisible to the greatest lower bound. But yeah, the great thing is that we actually, we have control over our partial order. So we can just say, introduce a type that is invisible to the greatest lower bound, and actually this is the top type. Top is greater than anything, so the greatest lower bound of top and anything else is anything else. And this lets us write this definition here totally mechanically. There's no thinking at all, after changing the ordering. This is a valid definition. This satisfies the constraints. This is con prime. And, right, it looks a bit weird. The calculations were a lot nicer. They were a lot cleaner. Well, there were less of them. But yeah, we can introduce some syntax as well. If we define this sort of wobbly arrow thing to mean precisely this, if something else top, it looks a bit nicer. We can also combine the last two together using the greatest lower bound because they had the same condition on the left-hand side. Great. This doesn't really answer the question about monotonicity, though. So why am I talking about this? So here is an observation. We can actually replace this double equals here with a less than. Why can we do this? Well, it still satisfies the same constraints. The reason is maybe subtle. It's not totally obvious in this presentation. It comes from actually the fact that we're sort of assuming the monotonicity of con prime. Don't worry, that's actually not a circular argument, but I promise. But this is cool because, for one thing, it lets us simplify the definition a bit. Okay, so these top two cases can be collapsed because if something is less than error, then it's also less than int, because error is less than int. So we can remove that case. And the really cool thing about writing it in this way, with this less than rather than this equals, is that we have monotonicity now actually for free. And so I claim that any function built up in this way using the greatest lower bound and this wobbly arrow is monotonic. For some intuition as to why this is the case, think of these clauses, so these sort of wobbly arrow clauses, as firing or not firing based on their condition. So for this to be monotonic, that means that if I have an s prime smaller than my s, then my con prime applied to that s prime should be less than applied to s. And you can see here that if I take an s prime which is smaller than my s, then at least the same clauses are going to fire due to transitivity. And the thing is that we are using the greatest lower bound to combine together all of these clauses, and that means that we're going to have at most the same type, but it could be less than it. So this is less than or equal to previous type, therefore it's monotonic. Of course, that's not a formal proof. There is a formal proof, but that's not it. But yeah, okay, the great thing is that all of our functions, all of our type checking folding operators, add prime, con prime, anything else we might add in the future, are constructed exactly in this way. Therefore, they're all monotonic automatically without having to do any additional calculations or proofs. So what we're left with is a little bit of a strange looking type checker. I've certainly not seen one written quite like this before. But once you get used to this sort of syntax, actually it's quite natural to read, I think. So if you look at this second one here, this add prime, which I've not shown you yet, but this is what you end up with. You can kind of read this really as, if both arguments could be an integer, then the addition of them could be an integer. That's the first clause. On the other hand, if either of the arguments could be a Boolean, then the result is a type error. And I say is. Technically speaking, this is could be a type error. But if something can be a type error, then it is a type error. I think this is called Murphy's law or Sod's law or something like that. So yeah, I mean, this is quite a cool approach. I think this gives us the monotonicity for free, which we needed to apply fold fusion to get our specification. We've got a few minutes. Yeah, so just to kind of take a step back and have a look at what we've done. We've sort of taken these, I guess, fairly standard compiler calculation techniques, and we've applied these to this new setting, which is type checkers. So we can compute a type checker from an untyped language and its semantics. Using these techniques sort of in the sort of plain standard way, we weren't totally satisfied. The calculations felt a little bit clunky, too creative, and we don't like being creative. It was a little bit unclear where some of the steps came from. And also this monotonicity issue, which is really annoying. And we fixed these things basically by looking at the algebraic structure of the problem that we had here. The fact that our specification really is fold fusion. And also looking at this partial order that we had to introduce in order to generalize the sort of standard techniques to our type checking situation anyway. And yeah, this has given us a really nice technique here, I think, that you can apply to various languages. Yes, in conclusion, this is a nice principled way to derive type checkers. I show you it on really a very simple language here. We only have three like AST structures, right? There's not much to it. In the paper, we do look at some slightly richer type systems with some subtyping and some slightly more complicated languages. Also, all of the proofs, all of the main results are formalized in Agda. So when I've said something like, trust me on this one, or this is not circular reasoning, I promise, this is why it's actually not circular reasoning. These techniques do apply more generally to what I've shown you here, as I say. So subtyping, for one. In some upcoming work, we also have looked at calculating typing rules rather than type checkers in somewhat a similar way. I think a very interesting way of looking at this as well, but typing rules rather than checkers, so not a function, but a relation. And I think that there's a lot of cool stuff, really, that you can look at in this area. Yes, I think, though, that's all I have for you for now anyway. Thanks for listening.
If I may, I'd like to ask a question.
Yeah, of course.
When you have these inequalities, always on the right-hand side is where your unknown sits, right, usually.
Where are we looking?
Like any of the specs that you have. Cond prime, when you're trying to derive that.
These ones?
It's on the right-hand side, right?
Sure.
And you needed to show, you needed to pick the best possible one in some sense, right? So there was still a little bit of creativity, it seems, because you had to, you couldn't just return error all the time,
Yeah.
right?
Yeah, this is a really good point. So, it is true that another valid type checker is just this function con prime ___ equals error.
Yeah.
One nice thing about the calculational approach, actually, is that as you go through these calculations, it exposes very clearly where your choices are. So it lets you come up with almost what you want, but it nudges you in the right direction of, these are the possible things you could write down. But secondly, where is it? So here, where we have this inequality at the top, which is con prime bull t prime is less than t greater slow than t prime. So what we do is we just turn this into an equals, and this is the greatest possible because any other thing that satisfies this would have to be less than that. So does that?
Yeah, so I was just wondering though, in a more complicated type system, could it be such that you may not pick the best possible one without realizing that you can do so? Like here it's very obvious that you should just turn the inequality into an equal sign.
Yeah.
But maybe, I don't know, when I finished writing a type checker for a complicated language, that I have picked the best possible solution to those inequalities.
Yeah, that's a really good point. I think I wouldn't be able to sort of say 100% I've done the calculations and I know that this is the best one. But it's actually worth pointing out that technically speaking, this isn't even the best one. So because we do actually have almost permission to add new types. And so what we could have done is added some sort of subtyping or some sort of dependent typing of, in this conditional, rather than giving a type error, we give like a union type. So I guess the answer maybe is not a very satisfying one, but it's that there's a lot of flexibility. The best possible definition, I suppose, would be to always just introduce a new type for every possible computation that you have. But that is a bit of a trivial solution as well. So I guess you always want something somewhere in the middle based on your needs.
Once you introduce top, don't you need to prove that top is never the answer from the type checker?
Oh, yes, good question. Sorry. I meant to mention that actually. No, it's a really good point. So you don't actually need to prove that, but it never will be the answer. And the reason is that if I come back to my specification, where's my specification? That'll do. So we're saying that the type checker is always less than the type of the value of evaluating it. And we know that no value has this type top, which means that if we're less than the type of our value, we're always going to be sort of below top. And since our type checker satisfies this specification, then that does suffice as a proof of this. Does that help?
That was a really fun story.
Thanks.
I want to tell you a different fun story related to the fact that Liam pointed out that you could just pick error all the time.
Mm-hmm.
So when I was writing my textbook, Programming Language Foundations in ACA, I was writing a type checker. Mm-hmm. And I started by writing one and proving if it gives you a type, the type satisfies the type rules. It's sound. And I did all that, and I just had to, I could have just always said false, and that would satisfy the specification. And then it hit me, oh wait, I can do a decision procedure. And then instead of arbitrarily making up error messages, the error message was a proof that this thing could not have this type. So that's a different way of approaching this than you did. It's not calculational, it proves the result sound, but this idea of, that hadn't occurred to me before, that what you want your type checker to be is a decision procedure for the typing relation is a neat idea, and it deals with this fact that it won't let you say it has no type unless you can prove it has no type, and then a proof it has no type becomes your error message, which is sort of cool. So that's just an alternate method. It'd be cool if you could combine that with your technique. I don't know if that follows or not, but I want to match your nice story with another nice story to maybe give a next place to go.
Yeah, thanks. That's a really nice idea, actually. I'd not thought about that so much before. I guess not to start a discussion in the Q&A time, but so how does this actually deal with not just giving error? Because couldn't I just, I mean, in this case with my conditional, if the branches have a different type, I sort of do want to give an error.
Well, the type rules in this case tell you that it only has a type if both branches have a type.
Oh, so is this sort of, you have typing rules and then...
In this case, I'm given the typing rules, right? I'm not deriving them.
Yeah. Yeah, it's possible that could be really interesting on this further work that I was mentioning, where we do come to calculate typing rules rather than type checkers, because then we're interested after that in deriving a type checker from these rules. I suspect it could come in there. Yeah, thank you.
Thanks. Excuse me if you already answered this, but does this scale nicely to deal with, I don't know, functions and function calls and lambdas and recursion? So
yes.
I read the paper, but none of those words are mentioned in the paper, so I wondered.
Thanks. Good question. Yes. So this exact technique does work with lambdas. We actually, unfortunately, had to take it out of the paper due to space constraints and reviewer comments. But I'd be really happy to show you how.
So there's an appendix somewhere?
There isn't, but I should put it somewhere.
You should put it somewhere, yeah.
I should put it somewhere.
Oh, and the reason I was wondering is because that your specification says, well, just evaluate the program. The spec is evaluate, compute its value and then take its type, right? But if it's a program that runs forever or that runs a very long time, that doesn't seem very feasible as a specification. So I was wondering how could that possibly work?
Yeah, so that is a really good point. So. And actually, this is why we moved on to calculating typing rules later on. So when we calculate a type checker with lambda terms using this particular technique, we had to limit the source language to just only terminating lambdas, which I think is a little bit unfortunate. What we essentially said is that we only have, so the argument to a lambda can only be like a value rather than another lambda itself, so, which is admittedly limited. Looking at calculating typing rules rather than calculating type checkers is, the techniques they're similar, but it does get around this problem quite nicely. So hopefully that's
Okay,
gonna
that might be
appear
better.
soon.
Yeah. But you don't want to take a technique that has a sort of fixed ceiling.
Yeah, yeah.
Just as great when Simon said, yes, publish all the work.
Yeah, I will. Thank you.
Yeah. Jin Zhang from McGill University. I think this approach has one, in a sense, maintenance problem in the sense that if you extend your type system, then you need to deal with the coverage problem because you don't know whether your current rules are actually covering or not. How do you deal with that kind of problem in general?
Wait, sorry, we don't know if our rules are what was that, sorry? I didn't quite catch the last sentence.
Sorry?
Sorry, I didn't quite catch the last sentence. We don't know if our rules are what?
Like whether you covered all possible types for, like, for example, for the cont prime. So, yeah.
Right, so that really we just get by here. We just, so it's essentially we do an exhaustive, so here we're doing the case of true booleans. We also do the false booleans, we also do integers. Essentially we just run this calculation for every value constructor in our language. So we have an exhaustive proof here. Does that sort of answer the question?
I mean, the cont itself is like defined in a covering way, exhaustive way, but like if you define the cont prime in the way you defined it, then when we extend cont, we might forget to extend cont prime. So in that case,
Right. If you redefine cond, you would have to do the calculations again, at least for the clauses that you've changed. Similarly, if you added a new value, you would have to then run the calculations for this new value constructor, but you wouldn't have to do the calculations again for everything else. So I guess it's something you have to be careful. There's no it won't tell you because it's you're just writing stuff down on a bit of paper, but yeah, you do have to be careful about that. Does that?
Hi. Have you thought about extending this approach to bidirectional typing?
Yes. Wow. Great question. Yes, we have. In fact, so that's basically my plan when I get back to Nottingham. Thank you. Thanks for that.
Hi. Have you considered the connections to abstract interpretation? Because it seems like, types can be considered an abstract interpretation, and monotonicity, having a lattice, these are all things that you might expect of your abstract domain. And it does seem like that's very similar to what you're doing in some way.
Yeah, absolutely. Good question as well. So this is very much linked to abstract interpretation. I'm not an abstract interpretation expert, but there is a link there. And in fact, there's a paper by, I believe, Kuso and Kuso, about calculating abstract interpretations, which I, to be honest with you, could not really make it through to the end. But it seems very interesting. I think that there's a lot of, I think that there's some very deep links here which are worth looking at, and I need to read more about, basically.
I think there is a paper also by Kuso, somebody related, on viewing abstract type inference as abstract interpretation.
Yeah.
So that's a great idea. It has to be looked at.
Yeah. Thank you. Yeah, I need to check these things out. I think there must be a lot there.
So in one of your earlier slides, you have the expression if true, then 5 else false. Mm-hmm. And that does not type check, or rather that produces the error type, because the greatest lower bound of int and bool is error. But you could argue that you can specialize the if expression to produce some type of int and bool. So have you looked into that? Because naturally, it seems that if you have an if expression, you really should have a sum type. And so rather than the greatest lower bound, which is like some kind of a lattice theoretic meet of these two types, you really should have a join.
Yeah, absolutely. Absolutely. And maybe this was another thing that we had to remove from the paper. Yeah, absolutely you can do this, and absolutely it works. And actually this comes back to what I was talking about a little bit earlier, sorry. Anyway, I'll find the slide. But it was where I say that this is the initial set of types, but we can refine this during calculations. And a refinement that is often very useful to make is exactly this thing, is sort of introducing sum types or introducing so various subtyping rules. And yeah, absolutely, this can fall very naturally out of the calculation as well, if you keep in mind during the calculations that you're allowed to modify this set of types. And this comes back to the earlier question of how do you know that you have sort of the most general type system? And the answer is you have the most general type system with respect to what you're allowing yourself to do during the calculations. So.